Hello my friends and welcome back to the Today Machine channel. The most marks the most significant stage in the modernization of Axiari Derona steelmaking complex, a decisive leap forward toward higher efficiency and product quality. At the core of this phase lies continuous caster, a new generation casting line engineered to deliver exceptional billet consistency and dimensional precision. Equipped with advanced cooling and control systems, it ensures uniform solidification and flawless internal structure across every cast strand. From the caster, semi-finished billets move seamlessly through a bypass tunnel for warm charge, a technological bridge that connects the steelmaking area directly to the rolling section. This tunnel maintains the ideal temperature of the billets, eliminating the need for complete reheating and drastically reducing energy consumption and production time. The process continues with a reheating furnace, designed for precision thermal management before rolling. Its high-efficiency burners and automated temperature control guarantee optimal heat distribution while lowering fuel usage and emissions. Finally, the transformation reaches the reversible sliding stand, a robust rolling unit that performs multiple passes on each billet to achieve exact dimensions and superior surface finish. Together, these integrated systems define the second phase as a milestone in Axiari Derona's evolution, combining innovation, sustainability, and precision engineering to set new standards in modern steel production. Titanium is a lightweight, strong, and corrosion-resistant metal that plays a critical role in modern industry. Its unique combination of high strength-to-weight ratio and exceptional durability makes it indispensable in aerospace, automotive, medical, and chemical applications. Titanium's resistance to oxidation and corrosion allows it to withstand extreme environments, from aircraft engines to marine vessels and chemical reactors. The production of titanium begins with the extraction of titanium-bearing ores, such as ilmenite or rutile. These ores are processed into titanium sponge through methods like the Kroll or Hunter processes, yielding high-purity titanium suitable for industrial and aerospace use. The sponge is then melted, cast, and refined in furnaces to achieve consistent chemical composition and structural integrity. Subsequent steps include forging, rolling, and extrusion, shaping the metal into sheets, bars, plates, or complex profiles for various applications. Throughout production, titanium undergoes strict quality control, including mechanical testing, chemical analysis, and non-destructive inspections to ensure reliability and performance. Its versatility allows engineers to produce everything from lightweight airframe components and medical implants to high-performance automotive parts and specialized industrial equipment. Titanium's combination of strength, lightness, and resistance to corrosion has transformed modern engineering. It enables safer, more efficient, and longer-lasting products while reducing energy consumption and enhancing performance. Its strategic importance in aerospace, defense, and advanced industries makes titanium not just a material, but a cornerstone of technological progress. At the heart of northern Italy, Axiari Derona stands as one of Europe's most advanced steel production facilities, an emblem of industrial precision and environmental responsibility. The journey begins with the arrival of 100% recycled ferrous scrap, carefully sorted and stored in enclosed yards to minimize dust and noise. This sustainable approach not only preserves air quality, but also sets the foundation for a cleaner, more efficient steelmaking cycle. Inside the melt shop, the transformation begins. Massive electric arc furnaces roar to life, melting tons of scrap under the supervision of automated control systems. The molten steel is then refined and guided toward the continuous casting machine, a cutting-edge installation designed to deliver flawless billets with superior surface quality. Each billet emerges at precisely controlled temperatures, ready for the next stage without any need for reheating. Through a seamless hot charging process, these billets flow directly into the rolling mill. Here, the rhythm of production intensifies. High-speed rollers shape the red-hot metal into wire rods and reinforcing bars, while intelligent cooling systems adjust the temperature profile for each steel grade. The rolling line, fully integrated with Industry 4.0 technology, ensures exact dimensions, perfect roundness, and consistent mechanical strength. Downstream, the newly built finishing line takes over. Coils and bars are straightened, stretched, and bundled using Danieli's direct rolling bundling system, a compact, high-speed innovation that streamlines production and enhances throughput. Sensors and digital quality control units monitor every meter of steel, guaranteeing uniformity and traceability from furnace to final product. Across the facility, digitalization plays a defining role. The Reload logistics platform tracks vehicles, personnel, and product movements in real time, eliminating internal congestion and reducing emissions. Data gathered throughout the process feeds into smart analytics, continuously optimizing performance and energy efficiency. From scrap to coil, every phase reflects precision, innovation, and respect for the environment. Axiari Derona has redefined what a modern steel plant can achieve, delivering strength, quality, and sustainability in perfect harmony, shaping the future of European construction, one billet at a time. Nakamura Tomei has established itself as a global leader in precision machining, offering a wide range of multitasking machines designed to optimize production efficiency, accuracy, and versatility. Each model integrates advanced technologies that combine rigid construction, high-speed spindles, and multi-axis capabilities, enabling manufacturers to handle a broad spectrum of parts and materials. The ACE 200 series is ideal for compact multitasking operations, blending, turning, and milling in a single setup. With a standard Y-axis stroke of plus or minus 41 megameters, milling capability, and high rigidity construction, the ACE 200 and ACE 200L models handlebar diameters up to 65 megameters while supporting tight tolerances in small to medium-sized components. Its small footprint and fast cycle times make it a strong choice for shops with limited space. The SC series offers a single turret multitasking configuration, emphasizing versatility and adaptability. It allows manufacturers to produce a variety of part geometries efficiently, making it suitable for both prototype and batch production. The NT Flex series pushes flexibility further, with dual spindles and dual turrets, featuring up to 24 stations per turret and extensive tool capacity. It excels in high-mix, low-volume production, delivering fast cycle times and reliable multi-process machining. NTH, EWT, and TW series are designed for heavy-duty turning, with dual spindles and reinforced beds, capable of handling long or large diameter components. The WT100, for example, offers dual 6,000 RPM spindles and high torque output, while TW models extend spindle-to-spindle distances for longer workpieces. The Y series focuses on high throughput, moderate diameter parts, combining dual turrets and simultaneous machining capability to maximize efficiency. The NTY3 and NTJ series feature advanced multi-turret architectures. NTY3 machines employ 3 turrets for extremely high throughput, while NTJ machines incorporate a swiveling B-axis turret for multi-face machining without repositioning, reducing cycle times and improving accuracy. At the high-performance end, the Mix and JX series deliver premium capabilities for large, complex components. Mix machines provide rapid cycle times, extensive tool capacity, and precise multi-axis operations, while JX machines combine large turning diameters, long spindle-to-spindle distances, dual spindles, and up to 120 tools, meeting the most demanding industrial requirements. Across all models, Nakamura Tomei emphasizes rigidity, precision, automation, and multi-process integration. Smart software, tool monitoring, and advanced axis control ensure high-quality production with minimal downtime. From compact as machines to high-volume JX centers, each model offers a tailored solution for modern manufacturing challenges, providing reliability, productivity, and precision in every operation. At Lucchini RS in Bergamo, every creation begins with material design, a meticulous selection of raw inputs, 88% of which are recycled. Each fragment of steel is chosen not only for its quality, but for its potential to be reborn. Inside the electric arc furnace, the metal faces volcanic heat, igniting a powerful transformation where science and sustainability converge. Throughout production, impact is measured and minimized, driven by advanced processes that refine precision and reduce waste. The steel is forged and heat-treated to gain strength, resilience, and a flawless internal structure. Each piece undergoes rigorous testing for purity and performance, ensuring it meets the highest engineering standards. From raw scrap to finished form, Lucchini RS produces steel designed for endless possibilities, shaping the materials that power innovation, mobility, and a sustainable future. At GBF, production begins with the seamless integration of forging and advanced R&D software simulation, ensuring every component is designed and crafted to exacting standards. The facility manages a brass and aluminum warehouse with storage capacity of up to 4,000 tons, supporting continuous operations and rapid material flow across production lines. Once raw materials are prepared, they move into heat treatment furnaces, all CQ19 certified, where internal T4 and T6 processes enhance mechanical strength and durability. This stage ensures that every piece achieves the required hardness, resilience, and structural integrity before machining. Precision continues with 17 high-performance machining lines, capable of shaping complex geometries with exact tolerances. Each part then undergoes aesthetic inspection and finishing, combining functional quality with visual excellence. Finally, finished products are organized in the finished goods warehouse, ready for dispatch or integration into larger assemblies. Every step reflects GBF's commitment to precision engineering, cutting-edge technology, and operational excellence, delivering components that meet the highest standards in performance, reliability, and finish. In the world of modern steelmaking, graphite electrodes play a critical role, serving as the conductor of immense electrical currents in electric arc furnaces. Their production is a complex journey from raw materials to precision-engineered components. Production starts with raw materials, primarily 100% imported needle coke and coal tar pitch, selected for their high purity and performance characteristics. The coke undergoes crushing to reduce particle size, followed by calcination, a heat treatment that removes volatile compounds and enhances carbon structure. Next, the material is pulverized, weighted, screened, and dosed. Coke is classified according to particle size and stored in separate silos to ensure uniform quality. The process continues with mixing, where the screened coke and binder pitch are kneaded together into a homogeneous mass, ready for forming. In the forming stage, the kneaded mixture is extruded through press nozzles to create green electrodes, which are then cut to precise lengths and water-cooled to retain shape. These green electrodes proceed to baking, a high-temperature treatment that carbonizes the binder, giving the electrodes initial mechanical strength. Following baking, impregnation enhances density and conductivity, after which rebaking ensures full integration of the materials. The electrodes are then graphitized at ultra-high temperatures, transforming carbon into crystalline graphite, optimizing electrical conductivity and thermal resistance. Post-graphitization, machining achieves exact dimensions and threading specifications. Each electrode undergoes rigorous inspection, verifying mechanical, electrical, and dimensional standards. Finally, electrodes are packed, loaded, and shipped, ready for use in electric arc furnaces. From raw needle coke to finished graphite electrode, the process combines precision engineering, high-temperature treatment, and stringent quality control, ensuring electrodes meet the demanding requirements of modern metallurgical applications. NNN. Graphite electrodes are the silent workhorses, conducting immense electrical currents and enabling high-efficiency melting. Graphite electrodes are manufactured through a precise, multi-stage process designed to ensure high strength, electrical conductivity, and thermal shock resistance. The workflow begins with high-purity raw materials, primarily petroleum coke and needle coke, mixed with coal tar pitch as a binder. These materials undergo crushing, calcination, pulverization, and precise weighing, followed by mixing and kneading to form a uniform mass. The kneaded material is then shaped into green electrodes, using extrusion presses and cut to specified lengths. Water cooling stabilizes the green electrodes before they enter baking furnaces, where the binder is carbonized, providing initial mechanical strength. Following baking, electrodes undergo impregnation to increase density, then rebaking to consolidate structure. Graphitization at ultra-high temperatures converts carbon into crystalline graphite, optimizing conductivity and thermal performance. Finally, electrodes are subjected to precision machining to achieve exact dimensions and threading, followed by inspection to verify mechanical and electrical properties. The finished products are then packed and shipped, ready for use in electric arc furnaces and other metallurgical applications. Graphite India Limited, a pioneer in carbon and graphite products, operates advanced manufacturing facilities spread across Nashik, Maharashtra, and other locations in India. The company specializes in producing high-quality graphite raw materials and synthetic fibers for industrial and chemical applications. Manufacturing begins with careful handling of graphite billets, which are transferred to vertical and horizontal CNC machines for precision cutting, turning, and shaping. Extrusion units are used for synthetic fiber and tubular graphite products, ensuring uniform density and structural integrity. Large hydraulic presses and straining machines form the material into final geometries while maintaining dimensional accuracy and mechanical stability. Quality control is integral at every stage. Components undergo mechanical testing, leak checks, and tempering evaluations to verify suitability for chemical processes, high-temperature operations, and electrical applications. Operators ensure careful handling throughout to prevent material damage and maintain employee safety. Assembly and finishing include painting, curing, and final inspection, with precise packaging designed to protect products during transit. Advanced instrumentation and master gauges are maintained and calibrated regularly to guarantee consistent quality, long service life, and process reliability. With integrated manufacturing, testing, and assembly, Graphite India provides optimized, cost-effective solutions across chemical, industrial, and engineering sectors, establishing itself as a one-stop technical resource for carbon and graphite products. The integrated production of tires combines precision, strength, and quality control at every stage. It begins with ingot section heating and descaling, followed by press forging on a 9000T press to shape the tire blank. Critical drilling operations are carried out on a 5000+ T press, after which the blanks proceed through the rolling mill, hot marking, and laser dimensional checks. Transfer tunnels guide components into heat treatment furnaces and quenching systems to enhance mechanical properties. Subsequent processes include tire cutting, laboratory sample preparation, and rigorous testing. Tensile, impact, hardness, and chemical analysis ensure material performance. Machining, magnetic particle inspection, and visual and dimensional checks confirm precision. Finally, the tires undergo painting, protection, and packaging, completing an integrated workflow that guarantees high-quality, durable, and reliable products for industrial applications. And arco u nanjas kt encephalevel bot gri. At Steelmaking, steel constructions come to life through a seamless combination of precision, technology, and craftsmanship. The journey begins in the painting and blasting chambers, two massive units measuring 30 meters long, 8 meters high, and 8 meters wide, where each steel component receives uniform surface treatment and durable corrosion protection. Spanning 500 square meters, the workshop is equipped with specialized cranes and advanced machinery, allowing large and heavy elements to be fabricated with remarkable precision. Every cut, weld, and fit is executed to the highest standards of quality and accuracy, ensuring structures that are both strong and reliable. Once fabricated, components move to the final assembly area, where even the most imposing structures, like ship loaders weighing up to 1,000 tons, are carefully aligned and assembled. Every stage is meticulously monitored, with Steelmaking providing support during no-load commissioning to guarantee flawless operation from the very first test. From surface preparation to precision assembly, every step reflects Steelmaking's commitment to perfect performance. Advanced technology, skilled engineers, and robust infrastructure work together to deliver steel constructions that stand as a benchmark of reliability, durability, and engineering excellence, ready to meet the demands of the most challenging industrial applications. The crafting of a 15-ton engine crankshaft is a process that relies heavily on the expertise of highly skilled machinists. Each crankshaft begins as a massive steel billet, carefully inspected for internal integrity and chemical composition. The machinist first assesses the billet for any surface imperfections or inconsistencies, ensuring the material is suitable for the extreme forces it will endure in service. The operator begins with rough turning, manually guiding the cutting tools to remove excess material and shape the crankshaft's main journals, crank pins, and web sections. Precision is maintained by frequent measurement checks, using calipers, micrometers, and templates to verify diameter and roundness. Each cut is performed deliberately, with the operator adjusting cutting depth and speed according to the material's hardness and temperature. This careful manual approach prevents deflection or vibration, which could compromise the crankshaft's structural integrity. After the rough machining phase, the operator performs finish turning, refining the surfaces to exact specifications. Each bearing journal and crank pin is smoothed, ensuring proper mating with engine components. Measurements are repeated continuously to maintain tolerances within microns, guaranteeing smooth rotation and balanced load distribution during engine operation. Once turning is complete, the crankshaft is transferred to a heavy-duty bench drilling machine, where precise holes for oil passages and balancing weights are created. The operator carefully positions the crankshaft and selects appropriate drill bits, controlling feed and speed manually to avoid cracks or material deformation. Drill depth and diameter are checked frequently to maintain accuracy and alignment with the crankshaft geometry. Finally, the finished crankshaft undergoes a visual inspection for surface quality, alignment, and symmetry. Any minor corrections are made by hand before the component is cleaned and prepared for heat treatment or assembly. This process highlights the combination of skilled craftsmanship and precise manual machining required to produce a 15-ton crankshaft. Despite modern automation, the operator's experience and careful attention ensure that each crankshaft meets stringent quality and performance standards, capable of enduring the extreme loads of heavy-duty engines. To achieve maximum strength, each aluminum wheel is crafted from a single solid billet, ensuring no part can break or detach under stress. It all originates from the cutting of the aluminum billet, using a carbide tool to produce the blank for a single wheel. Each blank is then heated in a furnace for 2 hours to approximately 500 degrees Celsius, softening the aluminum for forging without melting it. Next, the rotary forging machine shapes the soft billet into a thin disc under extreme pressure. This step not only forms the wheel but also realigns the aluminum's molecular structure, creating a stronger, more durable material. After forging, the wheel cools to room temperature and passes through a precision rolling machine, where massive rollers refine its shape. Cooling fluid reduces friction and aids in forming. The wheel then undergoes reheating to 530 degrees Celsius, which further strengthens its molecular structure before being quenched in cold water, effectively freezing the enhanced structure in place. CNC-controlled cutting tools carve the wheel's contours, including spokes and bolt holes, balancing style, functionality, and airflow for brake cooling. Finally, each wheel is meticulously inspected for roundness, angles, and dimensional accuracy. If it passes all tests, buffers polish the aluminum to a mirror finish, producing a high-strength, precision-engineered wheel ready for safe, long-lasting use. The TX Hoist series is engineered for industrial-grade lifting, offering capacities from 3 to 100 tons, with precise control over load handling. Each unit features a continuous-duty, inverter-rated gear motor, with totally enclosed fan-cooled design and Class F insulation, providing reliable torque and extended service life. Hoist speeds range from 8 to 80 feet per minute, while trolley and bridge speeds reach 35 to 200 feet per minute, enabling efficient material handling across production lines. The heavy-duty trolley frame is constructed from ASTM A500 steel with reinforced wheels, ensuring structural rigidity and smooth travel under maximum loads. Advanced control systems manage acceleration, deceleration, and load positioning, while optional configurations include magnet duty, parallel mounting, and custom applications. With rigorous mechanical testing, brake performance verification, and adherence to duty classifications, the TX hoist ensures precise, safe, and repeatable operation, making it suitable for demanding industrial environments requiring high safety and performance.